Alright, calc students, we're going to look at this function f of x is equal to sine of x divided by x. And what I want to do is point out, first of all, that this function is not defined everywhere. We have a problem because we've got a fraction and the denominator of a fraction cannot equal 0. So the function is not defined when x is equal to 0. And we can take this one step farther and look at this and ask ourselves, what happens if you plug 0 in for x? You end up with the sine of 0 divided by 0, which is 0 divided by 0, which really isn't 0 or undefined. This is something unique called indeterminate form. It's called indeterminate form because you can't determine if the answer is 0 or if the answer is undefined or what have you, because hopefully you agree that if you have a number like a divided by 0, that's undefined, but if you have 0 divided by some number, that thing is defined as 0. So if you've got a 0 on the top and the bottom, you can't determine what's going on, which is why it's called indeterminate form. So let's go ahead and put this conversation off to the side and talk about this function and what happens as we get really, really close to 0. So I'm interested in knowing what's happening as I approach 0 from both sides on this function sine of x divided by x. And I want to do this numerically, so not graphically. I want to actually look at numbers and figure out what's going on as I get close, and in fact infinitely close. That's what this says, as x gets infinitely close to 0 from both the left side and the right side. In the last video we talked about direct substitution, where we can take this number and plug it in to our function for x. But remember that that only works when the function is continuous at the point that we care about. And we've already talked about how this function has a problem. It has a discontinuity at 0, so I cannot use direct substitution. So we're going to look at a table of values, just like kind of xy values. On the left, I've got my x values, and here I've got my y values, my output values, my function values of sine of x divided by x. And what I want to do is remember that x is getting infinitely close to 0, so I'm going to arbitrarily start somewhere. I'm going to choose 1. I'm going to start at 1, and I'm going to plug in values of x that get closer and closer and closer to 0. So from 1, I'm going to go to 0.5. And I'm going to go ahead and keep on plugging in values of x that get smaller and smaller and smaller and are getting, in fact, closer and closer to 0. 0.001 is, you could say, very close to 0. And we could pick more numbers if we wanted to, but we're going to start with this and look at what happens. So the first value, 0.8414709885, we got that by taking 1 and plugging it in for my x value into sine of x divided by x. We took sine of 1 divided by 1, plugged that into the calculator, and got 0.8414709885. So as we keep plugging these numbers in, look at what's happening. We've got 0.95, 0.998, 0.9995. These numbers appear to be going somewhere. And if we finish out this list, we've got a really clear idea of what's happening. 0.9999983, however many nines there are there. We are getting very, very close to what appears to be 1. Now, we're forgetting something. What we've done is we have just come from 1 and we've gone to 0, so we have essentially taken a right-hand limit. We've come from the positive direction, and in order for us to verify that the limit of this actually is 1, we need to check the left-hand limit, because if the right-hand limit and the left-hand limit are not the same value, then the limit fails to exist. So here we go. We're going to look at the same values of x, only the negative version, so that we can see what happens as we come from the left-hand side. So here are my left-hand values getting really, really close to 0. And when I plug in the first number into my calculator, I see that I've got the exact same first value as I had over here. So there we have it, the rest of our values as we've plugged them in. And what we're seeing is that the left-hand limit and the right-hand limit appear to be the same. We're getting infinitely close to 1. So it does happen to be the case that the limit of this function as we get infinitely close to 0 is equal to 1. So really quick, let's just look at what we did graphically to confirm that we are correct. So what we just did is we looked at an x value of, we started out with, let's see, we started with x is equal to 1, which the graph that I have just created I've made increments of pi. So 1 would be roughly here, and we got an output value of 0.84, so that would give me a point roughly there. At 0.5, when x is 0.5, I've got a value of 0.958. And as I get closer and closer to 0, my values get really, really close to 1. Now remember that at the value of 1, there's a gap. There's a hole. It's not defined. But what this function looks like is a trig curve of sorts. That's not very beautiful, but that is what it roughly looks like. So what we've just confirmed is that as we come to 0 from both sides, we are getting infinitely close to a value of 1. Now, perhaps what you're wondering is, why can't we just take 0 and plug it in and plug it in? And when we do that, we've talked about how we get 0 divided by 0, and isn't anything divided by itself equal to 1? And the answer to this circles back to what we talked about at the very beginning about indeterminate form. 0 divided by 0 does not equal 1, and in fact, soon we're going to look at other examples like this, where we get 0 divided by 0, but instead of getting 1 like we got in this example, we might get a different number like pi or 2 or 10. So just because you get 0 divided by 0, that does not mean always that the answer is 1. It happens to equal 1 in this case, but not every time. Okay, let's look at another example. If we approach this function, x minus 9 divided by the square root of x minus 3, as x approaches 9, let's consider what happens at first if we just try plugging in 9. Let's look at what happens if we take 9 and we plug it in for x and plug it in for x. So if we do that direct substitution method, we get 9 minus 9 divided by the square root of 9 minus 3, which ends up becoming 0 divided by 0, which we've already talked about is indeterminate. We cannot determine what the answer is. 0 divided by 0 does not equal 1. It does not equal 0. It does not equal undefined necessarily. It might be one of those things, but we have no way to determine at this point what it is. So we are stuck. We can't use direct substitution, and this just goes to verify the fact that we can only use this when we don't have a discontinuity. If we consider the graph of this function, it's discontinuous when the denominator equals 0, which happens at the point when x is equal to 9. So we have a discontinuous function. We cannot use direct substitution. So we have to consider a different method. So here we go. We're going to do a numerical analysis because we can't use direct substitution and we're not graphing it right now. So here we go. I've made a table just like we looked at before. I have x values and y values, and I'm going to begin just like I began to the last one, starting from the well, actually, let's go from the left-hand side first this time. It doesn't matter if we go left or right first. So these will be our these will be our left-hand values. So remember, we're trying to come at the point 9 from the left-hand side. So start by thinking about numbers that are to the left of 9 on a number line. So 8 is the first integer to the left of 9. I'm not going to go to 8. I'm going to just start at a number that's closer to 9 already because I'm trying to get infinitely close. So let's just go ahead and start at a number like 8.9. And then we'll get closer and closer and closer. 8.99, 8.999, 8.9999. We're getting super close. I could do this for the rest of my life, but at some point we're going to see a really clear pattern emerge, hopefully. So let's start plugging these values in and see what happens. I'm going to take 8.9 and I'm going to plug it in for x and take 8.9 minus 9 divided by the square root of 8.9 minus 3. And when I do that, here's what I get. And already we can kind of see that we're really, really close to a number. If I asked you to round it up, you'd be rounding up to 6, right? So let's see if we continue plugging in these numbers. Let's see if we actually do, in fact, get close to 6. And there we go. As we go down this line, these numbers are getting increasingly close to 6. The gap between those numbers and 6 is getting infinitely small. And so it appears that as we approach 9 from the left-hand side, the one-sided limit there is 6. So what we need to do is confirm that that limit is the same from the other direction. And if it is, our limit will be 6. So as I'm trying to decide what values to choose to come at from the right, I'm going to use the same logic. I start at a 10th to the left of 9, so I'm going to start a tenth to the right of 9 this time, and then move down the line and get closer and closer and closer to 9. And there we go. Let's start plugging in some numbers. And there we have it. So our numbers are getting closer and closer and closer to 6. We end here with 6.0000, which is very, very close to 6. So this evidence would suggest that the limit as x approaches 9 of my function x minus 9 divided by the square root of x minus 3 is going to equal 6, which we never would have guessed if we had followed our direct substitution analysis.